Okay, welcome to the third and last week of the Bootstrap meeting. This week we are in coexistence with a strings meeting as well, so there will be more worldsheet people to discuss with, so take advantage. So let me just remind you, if you arrive now, that you need to use your name tag, because we can use the building in the afternoon, the other building at our will, so it's good that we have our name tag so that they can identify who we are. And vouchers, ask people that were here last week. That's most people, how it works, but basically vouchers are worth money, so don't lose them, and just keep them with you, and you can use them in 3 restaurants that are listed on the website. Finally, we started experimenting first week with parallel talks, which was, I thought, a great success, so we did it the first 2 weeks. This week we are going to have 1 parallel session, not 2, on Wednesday, and we have 1 free slot. So if you would like to volunteer someone or yourself, let us know. We have 1 slot out of 4 free for that Wednesday morning. Very good. So now I'll pass it over to the chair, Leonardo.
Okay, thank you. So we are very happy to have Silviu tell us about supercurrents and partial supersymmetry in 2-dimensional joint QCD and generalizations.
Okay. Well, I thank the other organizers for inviting me for making me give a talk. So I'll be talking about a paper that came out a couple weeks ago called Supercurrents and Partial Supersymmetry in 2D Adjoint QCD and its Generalizations, in collaboration with Igor Klebunov, Benjamin Sogard, and Edward Witten. And I'll also mention earlier work also in collaboration with Ross Dempsey. The motivation for this work, just to introduce this theory to the adjoint QCD, the motivation for this work comes from the problem of confinement and mass gap in 4D Yang-Mills theory, which is hard to solve. So then the strategy, or one strategy, is to look at toy models and toy models, well, so the non-abelian gauge theories, if we start changing things, then we can change the number of space-time dimensions, and in 2 dimensions, theories are simpler. So maybe we can start there. So what kind of non-abelian gauge theories are there in 2 dimensions, just to give you a sense. So the simplest thing is just pure gauge theory, so 2D Yang-Mills. Then the next more complicated thing you could have would be the 't Hooft model, which is 2D Yang-Mills theory coupled to a fundamental Dirac fermion. And these theories are quite simple in some sense. 2D Yang-Mills is very simple. Everything can be computed. The 't Hooft model was solved at large n, solved by 't Hooft in the 70s. So the next more complicated thing would be this adjoint QCD theory, where we replace the fundamental Dirac fermion with a fermion in the adjoint representation of the gauge group. Now the adjoint representation is real, so we can take this fermion to be Majorana fermion. So this is where this theory, adjoint QCD, sits, and it's sort of a better analog of higher dimensional gauge theories, because so in 2 dimensions the gauge field doesn't have any dynamical degrees of freedom. So if you want something that resembles 4-dimensional gauge theories, you'd want degrees of freedom in the adjoint representation, and fermions are simpler than scalars in 2 dimensions, so having an adjoint Majorana fermion would be the simplest case. And this is, unlike the 't Hooft model, this isn't solvable even at large n. And the other motivation for studying this theory is that if we're interested in studying confinement, we would like a good criterion for confinement. And gauge theories with adjoint matter in any number of dimensions have a precise confinement criterion. And this is the based on the expectation value of the Wilson loop in the fundamental representation. So the criterion is perimeter versus area law for the expectation value of the Wilson loop in the fundamental representation. So of this class of theories, adjoint QCD in 2 dimensions is the simplest to study. So that's another reason to focus on this theory. Questions already?
The question is that in 2D,
Yeah.
The Coulomb field already grows linearly.
Yeah,
So it doesn't naively, like, it feels like everything in 2D confines.
that's right. Yeah. So in 2D, the Coulomb potential grows linearly with the distance. So naively, one would say, oh, maybe everything confines, but that's not true. This will actually happen in this example. I'll mention it in a bit. Yeah. So it's a little more subtle than just that. The quantum fluctuations can change this. Now, so I'm going to focus on a particular 2D theory. Now, these class of 2D theories, in particular this one, could be another motivation would be a good playground for either numerical algorithms, and I'll mention results of numerics. So, for example, Lycon quantization, discretized Lycon quantization, or DMRG, various other methods, lattice gauge theory. And it's also studying 2D gauge theories is also a good playground for new or for various QFT ideas. For example, non-invertible symmetry, anomalies, and so on. So what will I show you in this talk? So this talk, it's a kind of weird QFT phenomenon, which is that at some values of parameters, and I'll say that very explicitly, there's supersymmetry, but the supersymmetry is not manifest in the Lagrangian description. There are no supersymmetry transformation rules that leave the action invariant. And I'll explain how this comes about. So that's sort of the motivation. Now I can get into this, what this theory is, and how the supersymmetry arises, and I'll mention some other features of this theory. Okay, so adjoint QCD2. There's an SUN gauge field, A mu, and a Majorana fermion that I'll call psi, 2-component. And the Lagrangian density is trace. So I'm thinking of these as n by n matrices. We can generalize a gauge group to any other gauge group, and everything I say still holds. So minus 1 over 2g squared f mu nu squared plus the kinetic term for the fermion and the mass term for the fermion. And this was studied by Igor and others in the 90s. And for what I'll mention also, David Kutasov did very important work on the supersymmetry. So this theory has two parameters, G and M. There's one dimensionless combination, so in 2 dimensions, the Yang-Mills coupling has dimensions of mass. So the dimensionless parameter is M over G. And we can restrict, we can take G to be positive. We can restrict M to also be positive because we can use an axial transformation. So psi goes to gamma 5 psi. So now let me explain my conventions. So I wrote down on the right of the right board my conventions. So I'm using this metric in plus minus signature. Gamma matrices, gamma 0, sigma 2, gamma 1 is I sigma 1. And then in 2 dimensions, we can have a chirality matrix, which I'll call gamma 5, skipping 2, 3, and 4. So that's gamma 0, gamma 1. So there's just sigma 3. So I'm using a basis in which the chirality matrix is diagonal. So now if we send psi to gamma 5 psi, the first 2 terms don't change, and the last term changes sign. Psi bar psi changes sign. So we can use this to restrict M to be non-negative. And the interesting values of M over G are M equals 0. And I'll mention what's interesting about them. M equals 0 and M equals G times square root of n over 2 pi. And this talk will be about the second one, this one over here. So that's the theory. Now, what are the properties? So before I say why these values are interesting, let me mention one other fact about it.
Sorry, probably
Yes.
a trivial point, but when you write these relations, you know, we have bare couplings, renormalized couplings. Is there some implicit choice of scheme? Or
The theory is super renormalizable,
and so we don't care.
so we don't care. Okay. Okay, good. Before I say what's interesting about M equals 0 and M equals this value, I want to mention that SUN is like one other fact about this theory. SUN has a ZN center, and nothing is charged. The fermion is in the adjoint representation, so it's not charged under it. So this Zn is a symmetry. It's a one-form symmetry. And what this means is that the Hilbert space splits under the action of Zn. And there's n sectors, call them flux tube sectors. They're labeled by the anality and I'll call the anality P, it's from 0 to n minus 1, of the electric field. So the trivial sector, we do nothing. The first non-trivial sector, we study the theory in the presence of a probe, fundamental, anti-fundamental quark placed at infinity, so we create a flux tube. And then we can put quarks in other representations, and we can generate all these other sectors. Unlike higher dimensions, in 2 dimensions, these flux tubes are Lorentz invariant, so we should study them as vacua of the theory. I'm realizing that this clock is not working, so I'm going to be completely lost. How many? 13. Okay, good. Good. And sectors. And with these flux tube sectors, one can say precisely what confinement means. So confinement, which is the same as area law for the fundamental Wilson loop, is the same thing as saying that the energy density in the p equal 1 sector minus the energy density in the p equals 0 sector, that's called the string tension, sigma 1. This is non-zero. And perimeter law means, well, sigma 1 is 0. Okay, good. So now let me discuss some of the features of this theory. So maybe some surprising features, and then I'll just focus on the one I want to talk about. So I said there are 2 interesting points, m equals 0 and m equals that value. So what happens at m equals 0? So at m equals 0, even though the fermion is massless, it turns out that the spectrum is gapped. So there's a mass gap. And even though from the Coulomb potential one would expect the theory to confine, that's not so. So in this case, the string tension vanishes. So these are the 2 surprising facts about m equals 0. That's why m equals 0 is interesting. So the evidence comes, well, from numerics. We can see, for instance, that the spectrum is gapped. Light cone quantization numerics or lattice gauge theory numerics. And the more conceptual reason is that in the d pi r, so when m equals 0, forget about the last term. So the theory is described by a coset model. So we have a in the numerator free fermions, and that's described, that's SO n squared minus 1. We have n squared minus 1 of them at level 1. And in the infrared, we're gauging the current, the SUN current. So we should divide by an SUN current algebra, and the level of the current one can compute it, it's n. So this is what IR physics is governed by. And this coset, their formulas, we can compute its central charge. And the central charge is the central charge of the free fermions. So n squared minus 1 over 2. Each Majorana fermion has C equals a half. And from that, we subtract the C of the SUN level n current algebra. And this calculation one can do, the formulas, this is 0. So that means that in the d pi r, we do not have a conformal field theory. We have a topological theory, and therefore it's gapped. And one can study this coset here in more detail, and one can find that in fact there are 2 to the n minus 1 degenerate vacua, a very large number of vacua. These are the states of the coset, and they're split among the different flux tube sectors roughly equally, and this would imply that epsilon p is equal to epsilon 0. So the energy density in the pth flux tube sector is the same as in the trivial one for any p. And in particular, that implies that these are, maybe I can add here, gapped vacua. So this argument shows both the gap and also the fact that string tension vanishes.
Good question.
Yes.
Is this similar to the Schwinger model? The fact that like in the Schwinger model, the photon acquires a mass, and you get the mass gap, and now you have short range interactions. Well, you don't have the SUN part, but is it a similar mechanism or?
The physics is similar.
Okay.
But how this happens, the details are much more complicated in this case. Yeah. And it took people a while to figure this out. So there's evidence. Well, the mass gap evidence from the numerics that dates back to the 90s, and also the arguments for the screening that also go back to the 90s. More recently, it was understood by Komargadsky and collaborators that the states of the coset transform under some non-invertible symmetry, and the non-invertible symmetry also explains the presence of the 2 to the n minus 1 vacuum. So that's m equal 0. Now the other value of the mass that I said is m equals g times square root of n over 2 pi, and I called that the SUSY mass because in this case there's 1, 1 supersymmetry. It was found by Kutuzov in '93. But as I mentioned, there are no SUSY transformation rules that preserve the action. This is what I'll talk about, the supersymmetry, for the rest of the talk. But before that, let's just say that for the other values of m, there's a mass gap and there's confinement. So in some sense, nothing interesting is happening. This is not surprising. That this is happening. So I want to mention briefly the evidence for supersymmetry. It comes from various sources, so I'll be very brief. I won't go into a lot of detail, because then I want to talk about what we did in the paper that appeared 2 weeks ago. Okay. So evidence for SUSY. So first piece of evidence, this goes back to the 90s, light cone quantization. So light cone quantization, x plus is time, x minus is space, and we do canonical quantization. Choose a gauge. So the gauge that people choose is the space component of A is 0. And then in this gauge, you can plug this into the action and see that A plus, the other component of the gauge field, and one of the components of the fermion, now let me explain my conventions. So, yeah, maybe I should have said when I said x plus and x minus. So I'm using light cone coordinates. So x plus is x0 plus x1 over root 2, and x minus is x0 minus x1 over root 2. Same for everything else with space-time indices. For spinners, I'm going to use this chiral basis, and I'm going to write the two-component spinner as 1 over 2 to the 1/4 times the top component. I'll call it psi minus, and the bottom component I'll call it psi plus. So the space-time indices, you can raise them and lower them with a metric, which if we use plus and minus coordinates, it's off diagonal. So the plus, upper plus becomes lower minus, and the other way around, with no extra signs. And the nice convention about the spinners is that a spinner minus index counts as half a space-time lower minus index. So when I write down write down equations, the number of lower space-time plus indices plus a half the number of spinner plus indices minus the number of lower space-time minus indices minus a half the number of spinner minus indices should match between the left-hand side and the right-hand side of each equation. So those are conventions. Takes a while to get used to, but they're actually the mass, psi minus psi plus, correct. Psi plus goes to minus psi plus. Just change the sign of one of them. Yeah. So if we use this gauge, so okay, I explain what x plus and x minus are, choose this gauge a minus equals 0, then plug it in the action, see that the a plus and psi plus are not dynamical. What that means is that they don't have any time derivatives, any x plus derivatives. So it's only psi minus that remains. And one can write down the momentum operators just in terms of psi minus. And then one can impose a cutoff on the Hilbert space and do numerics, for example. So the first evidence is from numerics. This goes back, again, it goes back to the 90s. And what was observed that this value of the mass is a boson fermion degeneracy. So if you look at the masses as a function of little m, so these are the masses of the particles. For the lowest particles, when m equals 0, there's a fermion here and a boson here. And as we change m, their masses change, and they intersect at this value, which is m SUSY. So this is the first thing, but then one can do better. And Kutasov and Burstein actually constructed this value of the mass. They constructed the supercharges. So Q minus, there's two supercharges, Q minus and Q plus. Q minus is integral dx minus 1/3 trace psi minus cubed. And Q plus is integral dx minus. This is going to look a little weird. So it's trace psi minus 1 over the derivative with respect to x minus, psi minus psi minus. Well, we're integrating out a plus and psi plus, so we can have things with we can get non-local terms. So these obey, so Q plus minus obey the 1,1 SUSY algebra. Okay, so that's the evidence from the 90s. So why don't we stop here? Well, because there are some Lycon quantization is a slightly weird thing. So let me explain what this does not capture. So maybe I can just say it in words to save time. Oh, I'm erasing the board. So one thing that light cone quantization does not do is that we cannot study these flux tube sectors. That's because of this gauge choice, A minus equals 0. We're stuck to a single flux tube sector, perhaps the trivial flux tube sector. We cannot study the other ones, so we don't get the full information about the theory. Another thing about light cone quantization is that the vacuum in light cone quantization is trivial, so we're not going to see the various degenerate vacua. And the other thing about light cone quantization, which is not a problem in this case, but in general it could be a problem, is because the equal time slices are constant x plus surfaces, and these are not Cauchy surfaces. This means that light cone quantization actually misses some particles. It would miss, we would not be able to see in light cone quantization the particles that are massless particles that are left moving. If any. In this case, there's none, but in the more general situation that I'll mention later, there will be. So one would like a better understanding, not just in light cone quantization. So second piece of evidence, it comes from Hamiltonian lattice gauge theory numerics. And this is, yeah. I can't repeat the question. Why can't you redo the analysis?
You said you don't see the massless left movers, but you see the massless right movers. But can't you just do the analysis with plus?
You can do the analysis with x plus and x minus swapped, and then you'd have the problem that you wouldn't be seeing.
But you can do both analyses, and then you see
you can do both analyses. Maybe this isn't like a serious criticism, but it's still something that we'd like to have a better handle on. So Hamiltonian lattice gauge theory numerics. So this is that I did with Dempsey, Klebanov, me, and Sogard. And this you can do only for small values of n, so just n equal 2 and 3. Of course, you can confirm this boson fermion degeneracy, but I want to mention one new thing that one can get from this, which is that now you can study all flux tube sectors. So you can study p not equal to 0. So if you look at p not equal to 0, something interesting happened. So if we look at the mass gap as a function of m. So in p equals 0, there's this, the picture is like here. P not equal to 0, the mass gap is like that. So it becomes 0 at precisely at the SUSY mass. So why is that, and why do I view this as evidence of supersymmetry? So why? Well, because I said that for all these values of the mass that are not m equals 0, the theory is confining. So that means that the energy density in the pth flux tube sector is not equal to the energy density in the trivial flux tube sector. So that means that in this flux tube sector there's some non-zero energy density. So that implies that supersymmetry is spontaneously broken. Spontaneous supersymmetry breaking. So this means that there's a massless particle, there's a massless Golstino. So this is the massless Golstino. This we could not see in light cone quantization because we don't have access to this sector. Third piece of evidence for supersymmetry comes from like a small circle. So you can put the theory on a small spatial circle, a small circle expansion. In this case, so if we compactify it on a small spatial circle, we get an effective quantum mechanics theory. And one can actually check that the effective quantum mechanics has supersymmetry at precisely this SUSY mass. So this is also work that I did with the same people. So this is the evidence that we had before this paper from 2 weeks ago. Any questions? Yeah, maybe. So we'd like a slightly better understanding. And the better understanding is the following. We can actually construct what the supercurrent is. So for supercurrent, so supercurrent, I'll write it as J mu A. Mu is the spacetime index and A is the spinor index. So this is from the paper from 2 weeks ago. So I can write down, we can guess, sort of guess what some of the components of the supercurrent are from these expressions. So J minus minus would be 1/3 trace psi minus cubed. J plus minus is some constant trace psi plus f. I'll explain the notation in a bit. So let me write down the other two. J plus plus is 1/3 trace psi plus cubed, and J minus plus is alpha, some number, from trace psi minus f. So here I'm using the fact that in 2 dimensions the field strength is a scalar. So I can define f is, I can define it by contracting f mu nu with epsilon mu nu. And we can also write this down here as 1/3 trace psi minus J minus. And this is 1/3 trace psi plus J plus, where J minus and J plus are the components of the SUN current, the thing that's gauged. So J mu is psi bar gamma mu psi, and it has components. J minus is psi minus, and J plus is psi plus, psi plus. Yes?
You said at the beginning that the action cannot be made manifest invariant, but
Yeah.
what if you just apply the Poisson bracket with this?
I'll explain what happens. Yeah. So the key is to check that the supercurrent's conserved. Maybe I can say that if we want to have a gauge theory with 1,1 supersymmetry in 2D, we obtain it from reduction of a 3D n equal 1 theory, and that under the reduction, the component of the gauge field along the direction that we're reducing will give us a scalar. So the field content of the most naive theory with 1,1 supersymmetry has a different field content. So the conservation is d plus j minus minus plus d minus j plus minus is equal to 0. And the other one, d plus j minus plus plus d minus j plus plus is equal to 0. So I'll focus on this. So the relevant equations of motion that you can derive from the action are d plus psi minus is minus m over root 2 psi plus. D minus psi plus is m over root 2 psi minus. And d minus f is equal to g squared j minus. So using them, we can compute d plus j minus minus. So j minus minus is just 1/3 trace I minus cubed, so only this equation's important. The factor of 3 cancels, so we get minus m over root 2 trace psi plus psi minus psi minus. And from the other one, d minus j plus minus. So the other component of a supercurrent has a psi plus and an f. So we can take derivatives of either one. So we have one term from taking derivative of psi plus, so alpha m over root 2 trace psi minus f, and alpha g squared trace psi plus psi minus psi minus. So it's clear from these two equations that this is not conserved using the classical equations of motion for any value of m and any value of g. So what did we forget? So but if we take this component supercurrent trace psi minus cubed, has a product of 3 fermions at coincident points, so it needs regularization, and the product of 2 fermions is singular, so psi a, psi minus a, psi minus b, a and b are the gauge indices, is minus I delta AB over 2 pi x minus. There's the identity operator, and so on. So this means that we need to regularize 1/3 trace psi minus cubed by point splitting. So 1/3 trace. But if we point split, we have to preserve gauge invariance, so we should insert small Wilson lines between the points. So psi minus of x1, u12, psi minus of x2, u23, psi minus of x3, u31, where uij is a small Wilson line, so what does it mean? So when we take the derivative, d plus derivative of j minus minus, the derivative could also act on one of these Wilson lines, and it will give an f. But the Wilson line is small, so this will be multiplied by epsilon. However, the product of 2 fermions goes like 1 over the distance, so that will cancel. So this procedure gives an extra term. So d plus j minus minus will be, the extra term is minus n over 4 pi trace psi minus f, and then we have the classical term minus m over root 2 trace psi plus psi minus psi minus. So this is the new term that comes from this anomaly of regularization, due to the regularization. So then we have 2 terms. D minus j plus minus also has 2 terms, so this is not correct. It's correct. And then we can check that the 2 are conserved, that the 2 add up to 0. So j mu a conserved if m is g times square root of n over 2 pi, and alpha is 1 over g square root of n over 4 pi. So this is the exact same procedure that is responsible for the axial anomaly in 2 dimensions. But it's applied to a different operator. It's applied to the operator trace psi cubed instead of it being applied to the axial current. There's the same diagram that gives this extra term over here. So non-trivial. It's conserved, but to show the conservation, one has to take into account this anomaly. So that's sort of like the main result about this theory. One can check. There's a supercurrent multiplet. And one can check that if we take the anti-commutator of Q with the various components of the supercurrent, we get the stress tensor with some normalization, and so on. So this supercurrent is related, is the same multiplet with the stress energy tensor of the theory. Yes?
Is supersymmetry manifest on the lattice if you set?
No. No, we don't know a lattice model with supersymmetry. Am I out of time? 15 till... Okay, good, perfect. So then let me mention now, in the last 15 minutes, a generalization of this.
Can I ask a question?
Yeah, sure.
Is there a way to think of this as supersymmetric deformation of the UV fixed point theory?
The UV fixed point being free fermions?
Well, I mean, with a free gauge field, I mean, I think it's not technically a CFT, so that's why it's maybe it's kind of...
The free fermion theory by itself is supersymmetric, but I don't know in what sense this is. You see, this alpha goes like 1 over G.
Yeah, but perhaps the deformation cannot be represented by a local operator.
Yeah.
But I was wondering whether there's some useful way to think in that terms.
Yeah, if there is, I don't know it. Okay, so then, so generalization. We can consider the following class of theories. Same thing, gauge field and an adjoint fermion, but in addition we can also add in some massless fermions. So add massless fermions Q alpha in some representation of the gauge group. Representation R doesn't have to be irreducible. So the Lagrangian density is the same as before, minus 1 over 2g squared f mu nu squared plus I psi bar d psi minus m psi bar psi. And in addition to that, we have q bar alpha d slash q alpha. And I'll keep these massless. So now the total current that's gauged is the current, the part of the current that involves the adjoint fermion plus the part of the current that involves the massless fermions that we added. So this one's the same as before, psi bar gamma mu psi. And this one is minus q bar alpha gamma mu t alpha beta a. I'm writing the components, q beta. And this current of the massless fermions forms a current algebra at some level k that can be computed from the representation of the fermions. So what this means is that if we take the OPE, j minus of x, j minus b of 0, the leading term minus k delta AB over 8 pi squared x minus squared, and so on. So this is the level k. It appears as a leading term. In the, sorry, these are the j tildes. So what's the physics of this theory? This is a little different because we added massless fermions. So the physics is that in the infrared, so if m is not equal to 0, if the adjoint is massive, then we can forget about the adjoint. So we just have the gauge field and these massless fermions. And in the infrared, we have, in general, CFT. So expect a coset CFT in the IR. What is the coset? Well, we have these fermions, so SO of the dimension, this is the real dimension of the representation R at level 1. This is free fermions. And we mod out by the current algebra at level K. So it's mod SUN level K. So in general, this is a coset CFT. And then one can check that we can modify our construction for the supercurrent in such a way that the supercurrent is still conserved, provided that we use, again, we use anomalies. So what is the modification? So the supercurrent so J minus minus is 1/3 trace psi minus cubed as before, and now we add to it trace psi minus J minus tilde. And J plus minus stays the same, so it's just some constant alpha that will now take a different value, trace psi plus F. And similar formulas with pluses and minuses swapped that follows by parity for the other two components. And one can check, like we did before, that this is conserved if m takes a specific value and alpha takes a specific value, and the value for m in this case is g square root of n plus k over 2 pi, and alpha is 1 over g times square root of n plus k over 4 pi. To check the conservation, again, that involves an extra term that comes from the regularization of psi minus cubed, and there's also an extra term that comes from the regularization of J tilde. This is really the axial anomaly, and the coefficient of that, so this one will come with the coefficient n, and this one will come with the coefficient k, and that's the reason why the mass involves this combination n plus k.
Can you get rid of the psi and just have the q's? Or?
You can get rid of the psi, and you can have the q's. In that case, there would be no supercurrent.
I see.
So maybe that gives a clue for what I'm going to say next. So I'll get to that. But I want to mention that this was also found in light cone quantization by Fedor Popov in 22. So the new thing about it is that appears when we look at the supercurrent multiplet. So, well, I should have said before that the supercurrent multiplet involves the supercurrent, the stress tensor, and there's another operator, which is a scalar, that doesn't play any role in anything I'm going to say. This is part of the multiplet. It's just trace f squared. That's what the operator is. The point I want to make is that if we take anti-commutators of Q with a supercurrent, we get a conserved stress tensor that I'll call T mu nu SUSY. That turns out it's not the same as the stress tensor of the theory. It will have quartic terms in the in these massless fermions Q. So the stress tensor of the theory is conserved. The stress tensor, the supersymmetric stress tensor that we get in the supercurrent multiplet is also conserved because the supercurrent was conserved. So that means that we have two conserved stress tensors. So this means that we can write T mu nu as the supersymmetric stress tensor plus an additional piece, delta T mu nu. And both T mu nu SUSY and delta T mu nu are conserved. And one can actually check that these two are two commuting stress tensors. Sort of the theory splits into two. A part that has T mu nu SUSY and a part that has delta T mu nu. I can write down what delta T mu nu is. So this is a computation that one can do. So delta T mu nu, I'm going to write down there's the first component, delta T minus minus, because it's going to be obvious what this is. So T mu nu SUSY, we get it from just acting with Q on this. So we know what the total stress tensor is. We can do the subtraction. So what this is I Q alpha dagger minus D minus Q alpha minus 4 pi over n plus k times trace J tilde minus squared.
Does that commute with the supercurrent?
This commutes with the supercurrent, yes. So this and then delta T plus minus is 0 and delta T plus plus is some similar expression to the one that I wrote above. So what is this? So this is the contribution to the stress tensor from the free fermions, and this is the Sugawara stress tensor, this over here, for the SUN level K current algebra, and this has the quartic terms. So this has quartic terms in the fermions. So this has quartic terms in the fermions. The SUSY stress tensors has quartic terms in the fermions. Combined, they cancel because the T mu nu doesn't have quartic terms in the fermions. So what are these? So then interpretation is this. Delta T mu nu is the stress tensor of the coset SO dim R level 1 mod SUN level K of the coset CFT. And in general, this is not supersymmetric. In general. Could be special cases. And T mu nu SUSY is the rest. So if we have the CFT here, what's besides the CFT? Well, some massive sector. So this is the stress tensor of the massive sector, which is supersymmetric. So in this case, in general, I would say that this theory has partial supersymmetry. It's got decouples into two. One part that's supersymmetric, the other part that isn't. And
can I ask a question?
yeah, sure.
So just to be sure, the coset, of course, is the infrared fixed point description, but but you're saying this delta T mu nu is conserved in the full theory, right?
I'm saying, sorry?
The delta T mu nu, you're saying it's conserved in the full theory, even though the coset is just the infrared fixed point description.
Correct, yes. It's conserved in the full theory, yes. So in general, partial 1, 1 SUSY. And then in the last minute, maybe I can try to answer the question, can we have full SUSY in a theory like that with additional massless fermions? So i.e., can 4 fermion terms cancel from T mu nu SUSY? So yes, if one of these two scenarios happens. So the first one is if the coset CFT that we thought was a CFT, so dim R level 1 mod SUN level K, if this somehow has C equals 0, so it's topological, then there's no CFT. So example, I mentioned at the beginning of the talk a case like this with massless fermions where C equals 0, and the example was just the adjoint QCD theory at m equals 0. So this would be SUN plus 1 massive adjoint plus 1 massless adjoint, the massive adjoint of a specific mass. And that's just because the CFT in this case is, the coset in this case is topological. And I see I'm really out of time. So the second, let me just mention the second option is, of course, when the coset CFT on SUN level K actually is a CFT that has supersymmetry. So this has SUSY. And as an example is SUN plus, I did not mention any CFTs that have SUSY, so I have to tell you one. So SUN with 1 massive adjoint, and if we add 2 massless adjoints, then this theory, that's just SUN gauge theory with 2 massless adjoints, is a 2,2 supersymmetric CFT. And if we add the massive adjoint of the appropriate mass, the whole thing will have 1,1 supersymmetry. So 2 remarks. One of them is the anomaly is needed in order to prove the conservation of the supercurrent, which is sort of the opposite situation from the one we usually encounter. We usually have a classical action that has some symmetry, and then we have an anomaly, and the anomaly destroys the symmetry. This is the opposite. The classical action doesn't have the symmetry. We add in the anomaly, and then the symmetry is there. So that's the first remark. And the second remark that's related to the string theory program too is that the adjoint QCD theory in the non-trivial flux tube sectors at the supersymmetric mass, so where the gap goes to 0, is an example of a fermionic string. So it's a string that has a Majorana fermion on it that's embedded into UV complete gauge theory. It would be interesting to study that further. Thank you.
Any other questions? Nathan?
So can you add some non-local term to Lagrange, make it supersymmetry?
Which one? Sorry.
So can you add an anomalous term, a non-local term to the Lagrangian so that it becomes supersymmetric?
That's a good question. I don't know the answer. I think the question is whether if one can have just a Lagrangian description just for the supersymmetric sector by itself. Then, yeah, I'm not sure.
Okay, welcome back. So, welcome to the second half of the morning. So, we're happy to have Andrea telling us about maximizing the interaction strength. The mic.
Okay, so thank you for, well, the other organizers again to invite me. Usual joke. So today I want to discuss a little bit about this recent paper, which I didn't have time to write it yet, the archive number. But I want to point out with my amazing collaborators, Miguel Correa and Alessandro Giorgudis, which they did a lot of work, and without them, we couldn't get this result I couldn't get this result for sure. And the archive number is this one. You will find it, okay. But okay, you'll find it. Okay, so, and to give you the idea, and this is the first work related to the non-perturbative matrix Bootstrap in recent years that address one regime of QCD, which is very hard to understand by any other means. So, and to explain this point, let me write a triangle of relations, which is always a good idea. And in a scattering process, usually, roughly speaking, you have two variables, S and T, the energy in the center of mass frame and the momentum transfer. And you can do basically a couple of things with these two variables. You can take S and T, both large, greater or equal than any other scale in your theory. And this is the hard scattering regime. And it's the regime in which perturbation theory applies, in which integrability makes a connection with the QCD, and it's the most well-studied regime. Then there is the regime of low energy, when S and T are order 1, or sometimes much smaller than 1, where 1 is your scale. And usually you can apply effective field theory in this case. And in this case, you can apply, for instance, lattice to study the theory, because we know that this scale is strongly coupled, because it's QCD. Dispersion relation, and recently, I have to say Bootstrap. So we are very happy that we got to this corner, finally. But there is another regime, which is very hard to understand theoretically, which is the regime of Regge physics, which is when, or soft QCD, which is when S is much, much greater than 1, and T is of order 1. And in this regime, there are not many tools, not many theoretical tools, because you see, energy is very large, but still it's very non-perturbative, because T is order 1. And in QCD, there is no dimensionless there is like only dimensionless parameters, not like in gravity, where G Newton, you can build dimensionless parameters combining G Newton, S and T, so you can a little bit trick this regime. In QCD, it's very hard, it's the hardest. So this talk will be about this regime. This talk. And just to give you like a little bit more flavor of how important is the regime, is that this hard scattering, let's say LHC, which basically takes care of these two corners, hard scatter, it's less than 1% of the all processes that happens in your collider. And all the rest is in this regime. So in particular, 25% is actually elastic scattering. So the protons, they just pass over. And the remaining 75% roughly is inelastic soft scattering. Okay, so inelastic soft processes. So you see this is like also the bulk of the processes that happen. So it's a very interesting regime, and this is what I want to discuss in this talk. And before going into the, let's say, into the, because for telling you everything I want to tell you, I would like to remind you a little bit what were the success what people understood in this regime. What are the success of Bootstrap in this regime? So the first and most important is, of course, the Froissart bound, which actually dates a very long time ago. I think it's 64, I think. And then there was some, well, now it's also called Froissart-Martin bound for a reason I'll tell you in a second. And maybe it's like 72. So it's some very old result, which still stands. And it tells you that if you take the total cross-section as a function of S, this quantity is smaller or equal when S goes to infinity to 4 pi, which is the strong coupling in any effective field theory, T naught, which gives you the dimension, it's some scale, and then there is a log square of S divided by some other scale S naught. And the 2 comes because we are in 4 dimensions. This would be d minus 2 in d dimensions. This T naught, usually it's related to the analytic properties of the process that you study. For instance, if there are no bound states in your, let's say, in your scattering process, this would be 4 times the mass square of the particle. But S naught is an arbitrary parameter. And in the last 50 years, roughly, people have wondered a lot about this S naught. If you move it around, you can raise and lower this bound almost arbitrarily. But this is the result that was derived, and usually the name of Martin is associated because Martin managed to prove it using all the axiomatic properties of scattering amplitudes. That's why. And well, to give you like a little bit more intuition, maybe for, I don't know how many of you are not familiar with this result, but of course sigma tot, this is a formula that I will need it later, is also related, and that's why we talk about scattering amplitude, to the imaginary part. So it's related to the imaginary part of your amplitude, 2, 2, 2, with momenta P1, P2, P3, P4. And it's related to the imaginary part of the amplitude when we set P3 equal to P1, P2 equals to P4, so that we are in the forward limit, divided by the flux of the incident particle, which is just a trivial square root, S times S minus 4. Okay, so this is the definition of the sigma tot. And clearly this quantity is positive. This is all we know. So this is all we know. It's a beautiful result. But now let me tell you about something else that people know, which is Regge physics. So something that people also know is Regge physics. And the motivation of Regge physics, I'm not sure if this is like an historic reconstruction, but this is the story that we reconstructed with Alessandro and Miguel. Regge physics is clear by looking, I mean, the need of Regge physics comes clear when one looks at this plot, let's say. Because this plot, in principle, contains the spectrum of QCD, where you see these massive higher spin particles that show up in your spectrum. And then if you have particles with this arbitrarily high spin in your spectrum, you would expect your amplitude T to contain terms of the form S to the J divided by T minus M square of the particle of spin J. And this is clearly much greater than S log square of S, which is the Froissart bound. So clearly, the presence of higher spin particles implies that you must have some Regge physics. You must do something to this amplitude. And, well, to make the story short, one upgrades J to be alpha of T, a function of T. In this way, your amplitude will behave like S to the alpha of T. The only thing that you have to care about is when this alpha of T, what value takes at T equal to 0. And here you see beautifully that one, if basically this is your J equals alpha of T trajectory now in QCD, the intercept is below 1. And we are all happy. right? Because we satisfy the Frossard bound, and we are all happy. And indeed, this value is 0.55. Okay, so this was like one of the first success of red geophysics, and in particular has been very soon experimentally verified when people could basically measure the total cross-section at colliders, for instance. And here you see some basically transient decay of the cross-section, because, okay, let me just set some notation. Sigma tot goes like s to the alpha of 0 minus 1, right? So this should go like s to the minus 0.45, if this is the intercept, so it decays. But then people started to observe already in the 70s that there was some growth here, a very slow growth, with the coefficient 0.08. And this what basically suggested that there must be something else in the spectrum that you don't see just by looking at the resonances, at the peaks in your cross-section. And this is basically what gave rise to the Pomeron. So this is how the Pomeron story was born, basically, to explain this growth that is not clear from this picture. So people started to imagine that perhaps there is some trajectory here that goes like this. And this is what is Pomeron. And the particles on top of this trajectory are not very visible, so we don't know yet what are the particles that belong to this trajectory. But now, what is the, let's say, okay, this may be some weak evidence for you, but then there are other measurements that confirm the presence of the Pomeron. For instance, is what people call the diffractive cone, that maybe many of you are not familiar. I was not familiar to these things before working on this project. So there is the diffractive cone. Diffractive cone is just the shape of the differential cross-section, d sigma elastic in dt, which decays exponentially in t. And this can be seen that is compatible with the red geophysics. It's very easily compatible with the red geophysics because if I remind you the definition of the elastic cross-section, which is just proportional to the absolute value square of the amplitude divided by a square. And then let's assume that alpha of t close to t equal to 0 behaves like alpha naught, don't want to commit to 1 now, alpha naught plus alpha prime t plus dot dot dot. And you plug this representation inside this formula, then you see immediately that you have like a beautiful prediction that this differential cross-section should behave like e to the minus some coefficient times t. And the coefficient is just 2 alpha prime log of s. Okay, so there is some fixed energy. So you see like here, for instance, in this plot, this represents the data taken at this energy at some collider, and I forgot which experiment. They show that the profile of the differential cross-section decays exponentially. So it's like some prediction. And indeed, one could measure alpha prime, and it was 20 Jev square, which is a slope different from the slope of the leading trajectory, what you would call the leading trajectory.
So it is, I didn't hear the sign. Is it the same or is it different?
Because t is negative in the physical region, so I just put absolute value.
No. I mean, your statement, is 20 compatible with the slope?
No, 20 is not compatible with this slope. So it's like half of the slope that you observe. And then another prediction of this formula is that this cone should also shrink as you go to higher energies. And indeed, it's logarithmic, the shrink. And in this plot, people raising the energy could see that the cone becomes like sharper.
Why is it called a cone?
Because like this is like some profile. I guess that you should imagine there is some other direction which you can rotate. I mean, here like I'm projecting on the plane. It's like a triangle, becomes a cone when you rotate. Yeah. Okay, I mean, it will become also clear later when I show the impact parameter representation. Okay, so this is basically the status. And this looks like a beautiful, consistent picture. But now I'm going to tell you a couple of things that makes this picture slight, not precise. So, and this is what, I mean, the point of this talk is about details, about fine details. So this is like a beautiful picture with a lot of nice predictions that were confirmed experimentally. But there are 4 points that we might want to raise that makes us a little bit unhappy with all this story. And now I'll tell you. Okay, so the first point is about this alpha naught for the Pomeron, which is not exactly 1, but is measured to be 1.08, and people happily quote this statement, which cannot be true, because t should go like s, not 1.08. So this is not really compatible with Froissart. So Froissart wants that alpha at 0 should be smaller or equal than 1. Then the second point is that if I maximize the cross-section at any point s, whatever is s, I can take s arbitrarily large, but I'm maximizing pointwise, then this is infinite. And this is okay, because the amplitude is a tempered distribution on the real energy. It's not an analytic function, so it can go to infinity.
Sorry, you maximize over what?
I just maximize the total cross-section at some energy s, and you can take it at any arbitrary energy, and it will always be infinite.
Sorry, I don't understand.
Yeah.
Is it a sorry, what are we maximizing over?
Well, okay. So if I maximize over the space of amplitudes that satisfy analyticity crossing and unitarity, you will get infinity at any energy. And this is compatible with the fact the amplitude is a distribution, so it must, I mean, there is no reason why it should be bounded, this quantity, point-wise. Then the third point is that if we take sigma for proton-proton scattering at square root of s equal 14 TeV divided by log square of s, so that it's just a number, this is something like 0.27 millibarn measured somehow, which is much, much smaller than what the Froissart bound predicts, which is this pi divided by 4 pi divided by 4, which is just pi. So pi divided mass of the pion, if you want, which is around 60 millibarn. So it's much, much bigger than this number, over a factor 100. And then the fourth, maybe, which is the most subtle one, is that Froissart growth, and by Froissart growth, I mean that if the amplitude grows like Ts to log square of s, then alpha prime t equal 1 plus, sorry, alpha of t equals 1 plus alpha prime of t cannot be true. So this cannot happen. Yeah.
In the item number 3, when you say log square s, don't you have to put in another scale s naught?
I'm being a bit sloppy here. I'm not sure what s naught I think they put 1 GV here to do this comparison, yeah.
Another question, do the data really can see the log square s? Because log square is a funny function. I mean, can we really see the log square behavior from the data?
So that will be, thanks for the question, will be the point that I will comment in a second. Yeah. It's really, so, okay, to anticipate what I'm going to say is that it's about to understand when the correction to this log square behavior kick in. And since this bound is only asymptotic, in this form you have little control on the corrections. But what I'm going to say now, which is the main result of this paper, is that we could put a bound on some behaved quantity, which is like some averaged cross-section, which makes sense, even at finite energy. And therefore, in this way, we could also, in principle, estimate the correction. We can see when the log square kick in, or the corrections are still important. And to anticipate, basically, from our analysis, it's clear that at LHC scale, the Froissart bound is still violated by at least a factor 2 or 3. So it's we are very far from asymptotic energies, even at LHC. Okay, so these are the 4 points. So
I'll also get to this, but François and Martin only said that there's an inequality. Should we believe that it's saturated by QCD?
So this is about this point. So how much can we say about saturation? And okay, this will be also part of the talk. Yeah, I wouldn't expect that it's saturated, but the coefficient is a bit arbitrary, is a bit large. We want to make all these statements precise. So that's our program, basically. Okay. So indeed, to summarize also the questions that have been asked, one reason perhaps why this is not consistent is because 14 TV is not asymptotic, and that's actually what happens. This is maybe okay, we need better observables. This is exactly the question that you already asked, like what about S0? This is not precise, want to make it precise, we don't know what is S0, we don't know like if this is optimal or why it should be optimal. This is all question we want to answer. And then about the last point, perhaps we want to propose a model in which maybe we can escape this argument that cannot be linear, the trajectory when you have Frost growth, and propose a model in which alpha of t goes like 1 plus alpha prime square root of t, and show that this is totally fine. Okay, so this is like the 4 point of the paper, of the talk also. Okay, so now I will summarize already part of the results since you already asked. And okay, I will start doing it up there because it's already relevant for this discussion. So as I was anticipating, the main result, one of the main results, is to introduce bounds on better observables, which are this smeared cross-section, which now are actual functions. And in general, you can think of them in this way, that I take, we can define them as like S bar tot with some smearing functional. Then we integrate from 4 to infinity in the S prime. And then here we can put some phi of S prime, sigma tot of S prime. And we could prove bounds on some class of smearing functions, of course, but the most interesting is when here you have like 1 over 16 pi. There is some, well, not that important factor, which is just kinematical factor, and there is like some step function, like this. So we smear the cross-section up to some energy lambda, and we can put bounds on this quantity. And what we did is that we put rigorous bounds on this quantity for any value lambda. And in particular, we focus on this class of smearing functions that we could also generalize to other smearing functions. Okay, so let me write it here. So these are bounds which are rigorous and model independent. And we could achieve this result only combining both the numerical S matrix bootstrap and some analytic arguments. So it's a combination of two ingredients, which I will explain in a second. And now, without spending too much time on the detail, just wanted to show you how the bound looks like, which looks very baroque, because we derived it in any dimensions. And we derived it, for instance, there will be some spin dependence L, which is totally arbitrary. There will be some energy scale T0, which is also arbitrary. And this bound is valid for any value of this spin, for any d greater than 2, and T0 between 0 and 4.
This is the spin of what? Of the external particle? Or?
Right, so no, this is just some arbitrary spin cutoff, which I will explain later. But this L, you can take it between 0 and infinity, the bound is always true.
I have a question. No, this D is the dimension, right? But earlier you said that you got leg squared because you picked D equals 4.
Yeah.
So, like, does the previous discussion about this bond still hold?
Yeah, I mean, here you will get, if we take the asymptotic limit of this formula, you will get a log of d minus 2 times s. Yeah.
Sorry, L minus 1, D minus 2 is the Pochhammer symbol?
Yeah, this is like a Pochhammer symbol. This becomes L squared in 4 dimensions, basically, L times L minus 1. Okay, but let's say the ingredients, I will describe it later when I do some sketch of the derivation of this formula. Here I just put all the details just because it's Baroque. I'm not going to explain all of them. This is just like decoration factors. What is important is that there is this Pochhammer here with spin, and there is this quantity, which is an observable that I will define soon, that you measure from the X matrix or from the amplitude. And this observable, which is some derivative of the amplitude at some specific point or some smart region, is positive. Okay, so this is like the kind of structure of the bound that we can do. But now let me draw some plot, because maybe it's a bit dry, the formula. So what we did, for instance, is like two things. Well, one we did and one we did yesterday. So now, since this bound is valid at any energy S, we can directly compare it with data. So there is no, we don't need to be afraid about any asymptotic. And indeed, what we observe is that right now we have some, so we'll put two plots here, one like this. So we can take the LHC data, so it's like sigma divided by S. This will be S in log scale, so here there will be like, I don't know, 10 to the 4 G square root of S in GV, 10 to the 4. Okay, all the way from 10, 100, 10 to 3, and so on. And we can basically exclude rigorously all the values of sigma divided by S which are above this line. So like excluded rigorously. Okay, and this has never been done before. We think it's a nice result. And well, of course, here the bound that I study is in terms of scalar particles. I didn't mention any spin. And of course, if you go to very high energy, then you might say, okay, but spin affects decouple. Perhaps there are some exchange of pions that you can neglect. Perhaps this bound is already good at the energy of the LHC. We don't know, but this is like working. I mean, it's like for the future. So in the future, we want to study the full system and make this plot more precise. For now, it's just a comparison to say that we can rigorously exclude value of the cross section which are above the experimental data at each energy S. Okay. And the second thing we can do, yeah. Sigma bar, yes, thanks. Thanks. And then the second thing we can do is, for instance, compare sigma bar tot divided by, let's say, S log square of S with actually the Froissart bound. So here I put log of S. And then you will see is that, well, let me set units such way the coefficient of Froissart bound, this pi is equal to 1. So here I set pi equal to 1. And then our analytic bound goes like this. Okay? And in particular, LHC scale is here. And what we see is that the bound is violated by at least a factor 2 or 3 at the LHC scale. And if we go to energy of 10 to the 30 GeV, and I remember that Planck scale is around here, so this is Planck, still we will be 10% away from the Froissart bound. Okay, so this is the result. So clearly this answers this question that whatever statement you make at LHC, this is very not asymptotic, and we should work harder to take into account subleading corrections if we want to make precise statements. So this is the first point. And incidentally, if we do this, let's say, if we use our bound, we are like an order 10 away from the experimental data. Instead of order 100, there are no S0, there are no funny factors, let's say. Okay. So this is like result number 1. About number 2, I already anticipated. I will derive this bound. At least, I mean, explain the logic, how that bound is derived and what it means. So 1 and 2 are answered. And then about 3, we only have a conjecture. So about 3 and 4, we go in the realm of conjectures. And what we can do, since we have the S-matrix bootstrap, we can also maximize directly this sigma bar tot as a function of S by varying on the space of analytic, crossing, and unitary amplitude. And now if you do this, what happens in this plot is that you can maximize, but you cannot go all the way to the bound. In the sense, the bound that you derive directly by using the S-matrix bootstrap is a factor 5 smaller. So it goes like here. So for each value of the energy we can maximize, we end up here. And then we can move the energy, we can choose another energy, maximize, we end up here, and so on. So this is what we believe should be the optimal bound. And the reason why there is this discrepancy between the two is because this is analytic, and it only uses some part of these assumptions, while this is numerics, and it uses everything. But then, of course, numerics, we cannot go to an LHC scale because it's too hard, so we are really restricted to some, yeah, we can only compare at small energy, the two bounds. Yeah.
So for the analytic bound, do you use rigorous analyticity?
Yes.
And the numerics, it's the row ansatz?
Numerics is the row ansatz, yeah.
Okay. And do you think the discrepancy could be because of that, or no?
No, no, there is no reason to believe that, yeah.
Okay.
Okay. So then, okay, now let me go to the wild conjecture. And the wild conjecture is basically asking what happens when S goes to infinity when you assume all these properties. And this we do it by basically constructing a sequence of functions, named that we run the numerics, in which we maximize sigma tot at some energy S, so we get the point. Then for each point, we get an extremal amplitude. So at this point, we'll get some amplitude A of S. And then we take the limit. When S goes to infinity, of this extremal amplitude. And we claim that this amplitude exists, first of all. It's called the Frossard amplitude. And it stays at some special point in the space of amplitudes, which is a cusp in the amplitude space. So let me make this plot, which is like the plot that also appeared in a paper by Liam, Dennis, and Chen, and also like by me, John Elias Miro, and Mehmet Gumus. Basically, this plot shows that the space of amplitudes in 4 dimensions is basically contained in this leaf, like this. And what we claim is that Frossard bound sits at this point. So this is what we identify as the most interacting theory.
So in which space are we plotting this leaf?
Thanks. So here, this would be the coefficient of phi to the 4. This would be the coefficient of d4 phi to the 4. And it's a projection. So of course, all theories are inside this, in this leaf. Okay.
And how do you set, is the scale setting by the pion mass? How do you inject the overall scale into your...
Yeah, it's set by the mass of the particles, which for us are scalars. They don't have to be pions. They can be any scalar. Yeah. Which from now on are set equal to 1. Okay. So this is basically the main result, and I will try now to at least explain these 2 points. So how we obtain this analytic bound, so the few ingredients that we need and the few steps of the ratio, which is simple. And then I will tell you about some consequences of this conjecture, like what we can learn by conjecturing that most interacting amplitude sits at this point, which is a very nice point. Okay, so now let me erase here.
Excuse me, I just have one more question. So these blue numerics that you drew, where do they sit on the plot on the right? The one where you put Froissart as some horizontal line.
These blue points, they will sit like here, close to the origin. No, I didn't plot it.
But are they above or below the Froissart bound?
No, they are clearly above the Froissart bound also.
Okay.
Yeah.
Thanks.
Yeah. I mean, this is just the coefficient of the Froissart bound, right? It's like the coefficient of the leading log in this, yeah. So that scale doesn't really make much sense to compare. Okay. So the derivation of the analytic bound is something I would say standard and simple. The only new ingredient is because we use an observable equivalent bound using the S-matrix Bootstrap. But the idea is that we take our sigma bar tot, okay, which is like some integral from 4 up to S, and then there is some integration variable ds prime, there is this trivial factors here, and then there is sigma tot of S prime. And the first thing you want to do is that you want to expand into partial waves. So you want to expand. And let me remind you that that we will always be okay with the partial expansion, because all the, let's say, all the values of t I will consider here are inside this region, which is the Martin potato. So let me draw the Martin potato, which is a region like this, where here there is 4, here there is minus 28, and there is some region like this. T equal to 0 is here, so it's okay. And the statement is that if you take fixed t, any fixed t inside this region, then the amplitude will be analytic in the complex S-plane with cut starting 1 at 4 and 1 at minus t. So I don't know, if t is here, then minus t will be here. Okay, so the amplitude will be analytic in this product for any value of t. So t equal to 0 is fine, we are okay. We can expand into partial waves. And then if we do it, well, let me do 2 steps at once. So I will expand, I will also split the sum. So we split the sum into L from 0 to L minus 2, plus L from L to infinity. And this is the same L that appears in the bound there. And here there are some trivial factors times 1 minus real part of the S matrix in some partial wave, like this. And now, this I call low energy, low spin. This I call high spin. And then we use these 2 tricks. One is to bound the low spin using unitarity. So we use the fact that 1 minus the real part of the S matrix is smaller or equal than 2. So you plug 2 here, you compute this sum and integral, and then in 4 dimensions, this just becomes low is smaller or equal than L times L minus 1. Very simple. And then for high, and this is basically the main point different, for instance, from what people did in the past. Because now I want to say it now, that people in the past, like, let me mention explicit, Indurain in the 70s, and more recently also Sasha 2020's Ziboedov, they used some observables which are not bounded from both sides. So the trick that we are using is that instead of expressing this sum of higher spins into some quantity that is not universally bounded, we use a quantity that we know it's bounded, we can show it's bounded rigorously. So this is the main trick. And the quantity is this derivative C2k at T naught, which, well, to explain you why we like this observable is because, first of all, is in the Euclidean region, so it's inside the Mandelstam triangle. So here let me put T, S, U, then this would be S physical region, U physical region, T physical. Here there would be a crossing symmetric point where S plus T plus U is equal to 4 and S equal T equals U equals 4/3. Crossing symmetric point. And then we can show that those derivatives of the amplitude taken along the SU symmetric line, this is like the SU symmetric line, are all positive. So since they are positive, they can be used to put bounds on this high spin tail. Okay, so these C2k are evaluated here. And they're all positive, they obey two-sided bounds. And because we write them into, let's say, along the SU symmetric line, they also obey some simple fixed T dispersion relations, right? Because now the dispersion relation will simply look like, so let's say C2 of T naught will be something like integral from 4 to infinity of the imaginary part of the amplitude at S prime T naught. And T naught is the Mandelstam triangle, so it's always inside this potato, so we're always rigorous. And then you have S prime minus 2 plus T naught divided by 2 cube. Very simple, like a very simple kernel, it is like 1/2 pi factor. And now we can expand into partial wave. So we can again expand this function into partial wave. Sum over L, trivial factors, 1 minus real part of the S matrix. There is some Legendre now. T naught divided by S minus 4. Okay, expand into partial wave. This sum goes from 0 to infinity. And now the simple thing to, let's say, the simple thing to realize is that if I truncate this integral up to S, and if I make this sum start from L, since all the quantities inside this sum are, well, except for this one, but all the rest that is known is positive, then we can just simply put an inequality of this form. And then actually we can also take out the Legendre. Using some simple inequality, we can take out all these trivial factors. And all in all, at the end of the day, we get that C2 bounds some trivial kernel, which depend on T naught and the spin, and the sum over the high spin. Okay, that's it. This is how the bound is derived. So then you can put all the terms together, and you get this formula in which you have the contribution from the low spin here, and the contribution of the high spin, which is bounded easily in terms of some quantity that instead is very hard to bound, this C2. But we can do it numerically. And if we do it numerically, so the last basically step to derive these nice plots, okay, we'll only erase this one on the right. So the only thing we need to plug into this formula to get a rigorous bound is the shape of C2 as a function of T naught, which is, well, max C2 as a function of T naught. Okay, so this is like T naught, this is 0, this is 4. And then the shape is something like this. Where here, it diverges like 1 over T naught minus 4. Okay, so this is like everything here is allowed. And then this plot here, so the actual bound is obtained numerically by basically optimizing over L, T naught, and, well, the value of this C2 at T naught. And that's it. This is basically the game that we played. Sorry? Very good. Yeah, thanks for the question. So, in principle, you would like to be agnostic about the actual polynomial, the power that bounds the amplitude, the polynomial boundedness, basically. In the sense that a priori you want to be agnostic. You don't want to say that satisfies twice subtractive special relation, but can grow like S to the n, let's say. And if it were to decay, if it were to grow like S to the n, that you need to use higher derivatives to write some positive sum rules. And then you basically you can show in this way that the best bound is actually obtained when k is greater or equal than 1, and nothing bad happens when you take k equals to 1. So we can derive for any k, but then we show that the best is k equals to 1, which is compatible with the Frossard bound and the twice subtractive dispersion relations. Okay. So maybe this was, I'm not sure if it was too fast or, but, well, perhaps one other thing I can tell you, I don't know if this helps to understand this asymptotic, how this bound behaves asymptotically, but when you go to large S, we can also take the saddle point in L. So we can show that, for instance, in this formula, L should scale like S, square root of S, log of S, let's say. And then if you basically show this taking the saddle point and plug it back, you get the Frossard bound back. This is just to say that our bound consistently tends to the actual Frossard bound when you go asymptotically. Okay, so this may be a comment I wanted to make. Yeah.
Sorry, I have a basic confusion. So there you show that the maximum of C2 diverges as T0 goes to 4. So why do you still get an upper bound on sigma bar tot? Yeah,
very good, very good. Yeah, very good. So this is not it's not totally trivial in the sense that somehow when you basically plug in, we have like I can tell you in a second analytic understanding, but in practice, what happens is that when we plug this shape inside their formula, then at each finite test, the optimal T naught is not 4, but is smaller than 4. So it's not optimal to take T naught to 4, even though this C2 diverges.
It's because of this KL term? So
it's because of the KL term, but it's also because you want to minimize this function. Right, so you don't really want to take C2 to infinity. Right, you want to minimize this function. If you take T naught equals to 4, this would give like right to infinity, would not be good. Okay? But numerically, actually, we see that we approach T naught equals to 4 because the Frossard bound asymptotically wants to set T naught equals to 4 asymptotically. So there is this little bit of tension between going to, that you don't want to go to T naught equals to 4 because there is divergence that you don't like because you want to minimize. But at the same time, T naught equals to 4 is what gives you the best coefficient in front of the leading log. So what happens to this tension? Well, this tension can be understood by looking at the sublinear correction, which perhaps I can just tell you briefly. So the sublinear correction, they basically look like let's say sigma divided by S log square of S will be 1 plus log divided by log plus 1 over log of S. And the dependence of C2 only enters here as log of C2 of T naught. This is like if you do the asymptotic expansion. So what happens, this is something perhaps we should clarify at some point because we didn't in the paper, is that when C2 of T naught approaches infinity with some rate in S, we can correct this coefficient here but we cannot correct this one. So in the end, it's innocuous, but this, yeah, it's a bit subtle. Yeah.
Thanks.
Okay. So, okay, this concludes the first part of the results, and now I'm on time, because now it's just speculation. So now I just want to justify why we like this amplitude here, and well, what we can learn looking at this amplitude about these points here, 3 and 4 maybe. Okay. So this I will keep it. Okay. So, this conjecture is wild. I didn't tell you why it holds, but maybe, I forgot to tell you, but maybe I can just say that as we numerically maximize the cross-section at each value of S, we basically see that the extremal amplitude has this coefficient that lie on a line that seems to approach this cusp. So this is like one piece of evidence, then we have another piece of evidence. But the conjecture is a bit, well, we have an intuition behind the conjecture, and numerically supported by some, let's say, not super strong numerics. But nevertheless, we can stare at this amplitude, and we can try to model some of its features. So how this amplitude look like? So the most striking feature is that if we plot it in impact parameter space, so if I put square root of S here, and I put B, which is just 2 times the spin divided by square root of S, then take a picture, like really a picture of the sky, then it would look like black everywhere, except for some strip here in the middle. So there is some strip in the middle. Here there is some garbage, let's say, but a clear strip in the middle. And what this is basically a profile of 1, so the color corresponds to 1 minus real part of S as a function of energy and impact parameter. And when it's black, it's 1, which means that it's just transmitting. But when it's white, it's -1, which means it's like reflecting. Okay, so you have like this picture in which you ramp in impact space. It looks like all black because it, lights just pass through, and then there is a strip in the middle where it reflects. And from this picture, we basically thought that this could be modeled by something we call the white ring model, which is a symbol profile in impact parameter space. So it's some S matrix, which looks like this. So imagine that I work at fixed S, right? As a function of impact parameter, there will be some R1 and R2. And then this function of impact parameter will be some R1 here, some R2 here. And then the S matrix is always 1, so always transmits. Then it reflects perfectly. And then it transmits again. Some profile like this. So this is what we call white ring. And now, if you plug this function inside the impact parameter representation, which I write you here because otherwise I will miss the factor 2 and I, so like 2is d minus 2b. It's basically the Fourier transform with respect to the momentum transfer, like this, and then 1 minus s of sb. So you plug this function inside this formula, and you get right away that this is equal to 8 pi is, there is a square root of minus t, and there is a difference between two Bessel functions. There is like R2, J1 of R2 square root of minus t, minus R1, J1 over R1 square root of minus t. So this is what this model predicts. That was basically just guessed looking at this impact parameter plane. And now, surprisingly, you can try to, let's say, plot this function against the Bootstrap data and see what happens. So if we plot this function is basically the Fraunhofer diffraction pattern. It has like some decay like this cone that I was saying. Then it goes to 0, and then there is some rings of diffraction, like this. And this is, if I compute the sigma elastic in the t as a function of t, using this model for some R2 and R1. But then, if I take R2 and R1 from this plot, let's say, and I plot the corresponding differential cross-section for the Bootstrap amplitude, for Froissart amplitude, then what you get is almost a perfect agreement, but the only difference is that the Bootstrap amplitude goes like a little bit up here. Doesn't have these perfect rings, basically. So this would be numerics, and this would be analytics. So you see this simple, basically this simple model, which you just take some ring and you plug it to the impact parameter formula, already gives you a non-trivial shape for this differential cross-section. And this is actually what is observed at LHC, in the sense that this seems to be a universal feature of these strongly coupled amplitudes. And at LHC, these rings, well, at least one ring is observed. So it's something that should be captured by any good model of energy scattering, even in nature. And now, well, another thing we can do, perhaps to address this point 4, is that we can take this function, and we can also play some game in the sense that we can go to s that goes to infinity. We can match with the Watson-Soffermeld transform, which looks like integral in the L s to the L times some partial wave. It's like a Watson-Sommerfeld, some anti-Mellin transform. And then you can match these two. And if you match these two, you get some partial waves for this model, which behave like 1 over L square minus 1 minus some constant square root of t to the 3/2. And if you expand close to L equals to 1, this is a bench point for L plus minus equal 1 plus some constant square root of t. So this model was derived just by looking at the impact parameter, which is in principle has nothing to do with, I mean, it has something to do with Reg. With Froissart, but we don't know. In the end of the day, it gives you some profile of the partial wave that has the square root of t behavior around t equal to 0. So it's compatible with this theorem here that I was mentioning here. Yeah.
Yeah, how do you reconcile this square root of t with analyticity in t? Because
well, this is analyticity in spin, right? It's not about analyticity in t.
Even this Reggie behavior, if you say alpha prime square root of t, then that introduces a cut at t equals 0, right?
No, you don't have to see it like this. You have to see that it's like a branch cut in the spin, not in t.
Sorry, maybe I can just say, I mean, that square root is not there. The 3/2 is a t. And then the solution...
Ah, sorry. You're right. There is a t. Sorry. You're right. Yeah. Sorry. You meant about this, yeah. You're right.
And you say L plus minus probably mean 1 plus minus.
Yeah, you just solve this equation equal to 0, and then you get 1 plus some number square root of t. That's what I meant. The branch point is in L, not in t. Okay, so this is very nice, okay, yeah.
said it, but is it obvious to see that the square root t gives you log square s, or does that take a little?
So to see it, you have to do this computation. So if you want to see that the square root of t gives you the log square of s, you have to basically, which is basically the step that is used to disprove this behavior. Basically, you take d sigma L in the t, you integrate in t, and this should be equal sigma L, and then by unitarity, this should be smaller or equal than sigma tot. So if you plug a model, a Regge model for the amplitude, inside this inequality with a linear slope like this, you would get some inequality of the form log cube smaller or equal than log square. That's basically how you say, okay, you cannot have linear. But now if you put square root and you compute these two integrals and you compare, then you get log square on both sides. So square root of t is compatible. But it's not the only possibility. Let's say it's just a feature. And this simple model somehow captures the simplest feature you can get. But now let me conclude with one plot, which is actually the spectrum of the Froissart amplitude. So let me conclude with this plot. I have 13 seconds. Can I have 1 minute? So now, if we actually plot this amplitude, what you will see is something like this. So this is the Ciufraci plot in which I put the spin, and here, here I put mass square, real part of the mass square of the resonances. Here I put the spin. And then what we see is that we see like 8 trajectories in total, one more crazy than the other. So one looks like this, then another one looks like this, and then there are 2 more, okay, which is something you might expect. But then there is one that is almost vertical. It almost touches, but okay, here I'm not drawing very nicely, but doesn't touch, then goes back. And then there are 3 on the other side, like this. You cannot see. You cannot see. Oh, this should see, because these are beautiful. Like this, red. Okay, cannot see. So this is spectrum that we observe, and we don't know if this is necessary or it's a numerical artifact or anything. What I can say is that we analytically continue in spin, and these trajectories, they form trajectories. So it's not some random set of resonances, but they form these families. And one of these families actually goes all the way down here, intercepts around t equal to 0 with alpha naught around 1.15. The subleading also intersect around 0.5. The leading does not intercept. The leading, we don't have a lot of resolution, but it seems that it joins with this one. So perhaps there is indeed the branch point somewhere here, although it's not exactly t equal to 0. And then on the left, there are all these crazy trajectories, which we have no idea what they mean. But we know that John Schwarz, before jumping into string theory, was working on this. He was like conjecturing that there might be many, many trajectories, and some also on the left, that could take into account for this funny behavior of the cross-section when it grows like Froissart. And with this plot, I will stop here. I think it's enough.
Any other questions?
And,
So you said that the numerics are most reliable for small s, but in order, so these I understand is the spectrum that comes from, like what the amplitude that maximizes the numerical bound, right? So what part of this plot can you trust most? Because I imagine like like you would need higher S in order to like.
Yeah, so the one that I trust more is this region here. Everything away from this region.
Sorry, the complement of this region?
Yeah, the complement of this region. This is what I trust more.
And that's what's controlled by small energies? Is that the idea? But
no, it's like a high energy, but somehow numerics converge faster in this region. Huh? I mean, yeah, I mean, we can enter into discussion about this point, but yeah. But I would trust more. No, but the reason, I mean, it's not crazy, because what happens is that when you go to this region where all the trajectories pile up, our numerics has a hard time to mimic all these peaks and dips that, you know, they basically all pile up in a region. But if you go to higher energy where they spread out, then numerics converge nicely, let's say. And what we see is that there is some instabilities indeed in these trajectories when you go in this region here. And then what Miguel mentioned is about this t equal to 0, and that's okay. That's a whole another, whole another story.
And other question, sorry. The second trajectory, does this match the row trajectory, or an F2 and so on?
Yeah, I mean, not really, because we are, let's say, yeah, to match the, so there are some qualitative matching, let's say, but you have to take the mass of the particle like 1 GeV, like lambda QCD. So there is some funny coincidences. If you say your pions are heavy like protons, then these slopes, they kind of make sense. What is nicer is perhaps that the ratio between these two slopes is almost the same as the Pomeron and the rho. So it's factor 2, which David Gross said it's like sister trajectories. So it must be something deep, but I don't know.
Thanks.
Can I ask a question? So these numerics close to this point are usually very hard. And there was a nice paper recently by Claudia and Andrew Tolle. Could you comment a bit on how their numerics match or not, what you are doing maybe in some regions? Or
So their numerics are basically the primal version of fixed dual, let's say. And I mean, so what we do is that we have exact crossing and maximal analyticity, and we only give up on unitarity. What they do is that they give up on crossing, analyticity, and unitarity. So they give up on everything, but then by sending all the parameters to infinity, you can hope to recover the full function. So that's what they do. I can give you more detail. They start from dispersion relations for partial waves, some integral in sum of imaginary part of FL with some kernel. And then once you start with this equation, if you like infinite equations of this kind, then you recover the full problem, because our ansatz already satisfies those equations. But if you truncate, then you have to send a number of equations to infinity. That's what I meant. Yeah, thank you.